Well, I'd like to say a few words about the homework problem. Most of you did pretty well on it, but there were a few points I'd like to comment on. The problem is a kind of an artificial one. It said that it posed a situation where there's continuous flow down a sluice channel, and normally the flow is reverse, the reversing flows, and you have to worry about the time change in currents and so forth. But the idea was to illustrate the process of making such a computation as simply as I could, in as simple a way as I could. And the easiest approach to it is to say that is to note that dm dt is equal to the depth times the change in concentration, which is minus the settling velocity times the concentration times 1 minus the shear stress on the bed and the critical shear stress. Most of you took from the handout, from the syllabus, the 0.6 that was found in the flume, which is perfectly all right. But I want to comment on that. You don't always have flume studies of that sort. Normally you have some inclination of the order of aggregation and the shear strength calculated from the cation exchange capacity. And I had thought maybe you would pick out one of the orders of aggregation and go on from there. Of course, you all received full credit whichever way you did it. But I noted on your paper that typically you start out with an order of aggregation. I would take first order, and that makes the bed second order, which gives the critical shear strength about 1.4 dynes per square centimeter. Or you might have picked second, depending on the circumstances. In any case, most everybody did that okay, and then the second step was to calculate the shear stress from U over U star. Well, let's make it this way. U equals U star times 5.75 log of 3.34 R U star over nu. And since I didn't give you any cross-section, you might take the depth, and most everybody did that. Or if you knew the cross-section shape, you could calculate R. Then find U star by trial, and then the shear stress on the bed is rho U star squared. And few people had any problem with that. But then the next step seemed to give considerable problems to people. You can calculate delta M, delta T, let's say, as equal to all of that, and come up with a number. Mass of solids, M is mass of solids, change in mass of solids per unit area of bed, right? So that's the amount of solid particles that settle to the bed. Now, to calculate the change in elevation of the bed, you need to know what that mass of particles does to that mass of particles does to the volume of 1 square unit area of bed. So for that, you need to get the change in elevation, let's say, of the bed. That's equal to delta M. This is delta T. Delta M, delta T, divided by the concentration of solids in the bed, right? In the bed, and that'll give you know the solids going down per unit of time, and knowing the concentration of solids in the bed, then that gives you the change in elevation of the thing. And the solids in the bed can be calculated from, say, the density of the bed is equal to C solids divided by the density of particles times And I gave you this. So he solved for C. And then divide, and that gives you the change in elevation of the bed. A number of you used the density of the bed, which has the same units. I mean, the units come out all right, but the density of the bed is the mass of solids plus mass of water divided by the volume of the sample. Oh, well, the reason for bringing this up this morning is that I wanted to make sure you're all clear on this concept. It comes up in virtually every computation of changes in bed elevation. On the previous, Tori?
I made the assumption that R was equal to D in my calculation, but based on your last lecture, it seems like maybe an assumption of a rectangular section would be better. I mean, a square cross section. Because last time you said that sloughs were really deep and narrow versus wide and
right.
shallow.
In sloughs, that's typically the case. They are deep-sided.
This was a slough, right?
Yeah, this is so.
R is equal to D
Yeah,
was kind of invalid
yeah.
in this case.
Sure, that's fine. That was good assumption.
I assumed R equals D, but I think it sounds like it isn't
But
really accurate.
yeah, but there was no width given.
Yeah.
Which
I'm
you,
saying maybe it would be better to assume that it was, say, a square cross section, and then,
if you had a width,
yeah.
but there was no width given in the problem set. If you had the width, by all means, yes. Any other comments before I go on to another?
Could you discuss when the paper is due, when?
Can I come to that in a minute? In the previous problem set, there was a question asking for a calculation of the bulk density, if I recall, from moisture content determination. And most everybody got the moisture part right, but when you evaporate moisture from a sediment sample, you leave the salt in the sediment. So the density of the solids isn't 2.65, including the salt. You have to add the mass of the salt left from the volume of the sediment, and you can calculate that roughly from the difference between the density of the salt water and the density of fresh water. Now, actually, it's not exactly that, and I'll have to point out that if you take a volume of water, carefully measure a volume of water, and add salt to it, a known volume of salt to it, the result is not the sum of those volumes. It's actually less. And the reason is that the water reorganizes itself around the cation in the salt. So if you add sodium chloride, then the water molecules collect around the sodium chloride, the sodium ion, and the density is greater than the density of bulk water. But that's usually not significant in a computation of this sort. Now let's see, the question about term paper, was that what you had? I'd like to have it on Thursday. Is that going to cause anyone a hardship?
Next week.
Yeah, not more than 5 pages, and include the bibliography, though. That's my concern.
You're talking Thursday next week or this week?
This coming Thursday, day after tomorrow.
Yeah, I'm going to have
Okay. Well, let's pick a time for everybody. How about Monday? This coming Monday? My concern is that I don't want the term paper to interfere with your preparation for finals. That's my real concern. When is final? I don't know when. I'll talk about that in just a minute. How about Friday afternoon at 5? Is that all right?
I won't even start on it.
Okay, get it to me by Monday. Everybody by Monday. And the term paper is not so important as your finals, your other finals. So I'm going to leave it to your managing your own time, but have it to me by Monday. Now about the final. I'll give you a take-home final Thursday. And I don't know when finals are scheduled for this class. Does anyone know?
Yeah. It's either Friday at 4 to 6 or it's Saturday morning.
Okay, well, that's the end of the final week, right? Okay. My only constraint is that I have to get the grades in shortly after the final schedule. They schedule the processing of the grades with the final schedule. So let's say I'll give it to you on Thursday, and you give it back to me by Friday night at 5 o'clock, a week from Friday night at 5 o'clock. Is that fair enough? Okay, we'll talk more about the final when I hand it out to you on Thursday. Today I'd like to talk about how to minimize sedimentation in harbor facilities, navigation channels, and at wharfs and in small craft harbors and so on. I've talked about this off and on all through the quarter as an illustration of various points. But now I'd like to kind of put it together in terms of general approach. I need to introduce the subject by saying that every harbor, every situation is a different situation. There are no two alike. I've never seen any two that I'd say, well, this is a carbon copy of something else. I need to do that. You always need to consider where it is, what the general transport is in the region, what the hydraulics are in the region, and often what the winds are in the region. So you need to consider the particular location and the conditions there pretty carefully right at the outset. Otherwise, you're going to be tripped up later. I can quote many people that work in estuaries, and they'll all say there are no two estuaries alike. In fact, sometimes the arguments you hear in conferences on estuarial or tidal hydraulics and sediment transport result from the fact that one person has an experience in Chesapeake Bay and somebody else has an experience in San Francisco Bay. The discussions are pretty lively, but when you boil them all down, it's because there aren't many people that have had experiences in a number of estuaries, and they don't recognize the range of conditions. And there is a huge range in conditions. In the Chesapeake Bay, for example, the main contributor of sediment is the Susquehanna River. And when a hurricane passes over the region, they get a big bulge of sediment, and all the rest of the time they don't get many. Well, a hurricane only passes maybe once every 15 or 20 years. So the sediments that come in at one particular time. There is some bank erosion that adds to it. But in general, there isn't much sediment in motion. So Professor, professor now at Stony Brook, when he was doing his thesis project, he thought aggregation wasn't important. Well, the concentrations that he was dealing with, it wasn't really important. But then he proceeded to generalize that. It's not important anywhere. Well, if you go to the Thames, where there's huge concentrations of suspended sediment, where it's worse than that bottle we had here, then it's the processes are really important, and in between they are. I remember a conference in the University of North Carolina where he got up and he presented a paper essentially saying that aggregation processes are unimportant to cohesive sediment transport. Well, I had come with a paper prepared, but boy, after hearing that, I sat down and wrote out another one and presented that. And we had quite a talk about different conditions and what's really important. Well, that's just an example of views that you get when people work largely in one estuary before they've had a chance to see many. And it emphasizes the point that estuaries are quite different from one another, and what you see in one estuary may be quite different from what happens to the other. So my point again is, be sure you look over the estuary, the general processes going on, hydraulics, sediment transport, freshwater outflows, and so on, so that you know the circumstances of the system you're working in. The next step is to look at what opportunities there are. If you can locate, if there's no harbor and you want to locate it, you're able to locate it, which rarely occurs, by the way, then you can find a place where there's very little sediment in motion, or where the scouring currents will keep it moving through, or places that are ideal. That would be the best solution. If we could go back and rebuild all our harbors We could do a far better job than has been done. But you can't move a harbor. You know, if one's built, there's a huge investment there. And tearing it up and putting in a new one is beyond our economic means for most cases.
Concerning the difference between geographic regions and harbor diversity, I can see certainly that the hydraulics regime would be different from in almost every instance. Well, what about the mineralogy? How much difference is there?
About the
mineralogy?
mineralogy?
Between the east
Yeah, that's a good point. The sediments that you find in estuaries, in most estuaries, and I'll give you some exceptions in a minute, are soils eroded from the adjacent lands, you know, lands in the watershed that drains into the estuary. So what you'll find is the kinds of sediments that result from those areas. Now, in warm, moist areas, you'll find clay minerals that are almost at the limit of their deterioration. There'll be iron oxides and aluminum oxides and laterites generally, or maybe kaolinites, which are well-weathered clay minerals. If you go to, say, the central part of the United States, where the clay minerals are largely montmorillonite, then they're all montmorillonite, practically all montmorillonite. The Mississippi Basin is practically all montmorillonite. The in-between North Carolina and that area is illites and kaolinites primarily. So if you look in the region, and you can look at the weather system and get some pretty good idea. If it's dry and cold, there won't be much, there may not be clays, it may just be silt. In Alaska, you find practically no clay at all, at least in the upper part of Alaska. But you find rock flour, which is 10 micron or smaller ground up rock, ground up by glaciers. And they're weakly cohesive, but they're not clay minerals. So generally, a particular area will have a particular kind of clay, and it's not hard to find out what it is. You go to the library and get the soils reports out, you know, on the local lands. And that will tell you. Get some samples and have cation exchange analysis run, and you can estimate the shear stress strengths and so on from that. But you're right, the sediments vary region by region. As I've pointed out already, the tidal hydraulics vary region by region too, because of differences in resonances, range of the tides, and difference in freshwater outflows. So those are big factors. If you have a wide tide range, say a 10-meter range in the tide, 30 feet tide range, you can bet that there's going to be a lot of back and forth motion inside the estuary. And there can be high concentrations of suspended solids if there's a supply there that's kept in motion because of those high tides. Whereas if you have a weak tide, like in the Gulf of Mexico, and a high freshwater outflow, you're going to have very sharp freshwater saltwater interface, very little movement back and forth, and typically not very high concentrations except when the drainage from the land brings high concentrations out. So you can tell a lot by looking at the land and before you ever get involved in a particular harbor. I just want to emphasize that before you get started in any particular problem, it's a really good idea to look over the area carefully, get some idea, find out what the tide range is, find out what the freshwater outflows are, if there's freshwater outflow, and what the wind patterns are, and so on, so that you don't overlook some significant factor in the design process. You'll find interesting things. In the mouth of the Columbia River, for example, most of it is sand because the wave action is sufficient, let's say from the mouth in the jetties up to Portland. It's pretty much sand. Some gravel in the middle part of the bed is sand, except in the side bays where there's clay on the places that are sheltered from the wind or wave action. And that clay can be a problem if you have a harbor right next to it and currents that flow out of the clay area into the harbor. Victoria, for example, Oregon has a real harbor problem because of clays that come out of Young's Bay right next to the harbor there. whereas the rest out in the main part of it, the Columbia River mouth, it's sandy. There was an interesting problem came up when the Portland District wanted to deepen some channels and add some new channels in that part of the mouth of the Columbia River. It's sand out there, and it's sand that's sort of waves. The waterways experiment, they modeled that area to predict what the dredging, the increase in dredging would be after they dredged it. Well, they didn't take into account the fact that waves stirred that sand continuously, and when they lowered the depth of the channels, the sand would funnel into it and reestablish the existing slopes. So that at first there'd be a lot of sand to it, and that would quit after a while, after the new slopes were reestablished. These overlooked, there's things like that that crop up. The system have a pretty clear picture of what's happening out there before you get involved too deeply in the details of the design. You'll save yourself a lot of time and errors. Well, the methods of minimizing sediment into channels and harbor facilities really boil down to two approaches. The first one is if sedimentation occurs, keep it moving on. Keep it moving through. You have sediment and other way, just keep it moving through, and I'll describe means of doing that. The second one is keep sediment out. If there's some way that you can wall it off or divert some other path, then by all means keep the sediment out. It's the suspended solids that cause the sedimentation. Suspended solids combined with the hydraulic conditions in the harbor area that cause the sedimentation. So either you have to keep it moving through or you have to keep it from getting there in the first place. Now, moving it through means minimizing the amount of sedimentation that occurs and providing currents that sweep out what does deposit. We're invariably dealing with a current that reverses, which means that it stops and picks up again. And during the times that it's moving slowly, material will deposit if it's in suspension. So you want to be able to move that back out. To do that, you provide shear stresses on the bed that will move it out at least once a day, at least once during every tidal cycle. And the reason for that is if they're in gels, it gets stronger. And we've talked about that. As you'll see as I go on today, what we do is just take advantage every way we can of the properties of the material and the hydraulic conditions that prevail to minimize the sedimentation rate. Well, with that kind of introduction, let me describe some examples for you that you've already seen actually some of them on our field trip, but I can describe them a little bit more. First thing I want to do is, boy, that's really dim, isn't it? Not very bright. Thank you. First thing I want to talk about is keeping it moving on. That's for large commercial systems, that's almost always the requirement. Here are two wharfs in Carquinez Straits. This is the mouth of Mare Island Strait. We visited the yacht harbor up here, Vallejo, and the Carquinez Straits Bridge is right here. This is Dike 12 that we saw going out into San Pablo Bay, and this is Rodeo. And this facility with the causeway out and platform is the Oleum Terminal Wharf. Now, the currents here are sufficient to make the strait really deep. It's 100 feet deep right about here, for example. And the currents out here are very strong also. So you'd expect a wharf placed parallel to the currents like that wouldn't have much of a dredging problem. Shouldn't. The currents are really high. The bottom is mostly sand, and it really shouldn't have much of a dredging problem. But they have to dredge it every other year. They have to dredge around. I'll explain why. There's a second one here that you can hardly see on the picture. It consists of simply dolphins, that is piles, a collection of piles at an angle with a concrete cap that ties the tops all together, and a catwalk between them. There's a dolphin here, another breasting dolphins here. That is collections of piles with shock absorbers, huge shock absorbers on the front that a ship hull can be tied up against and held there without damaging the hull. And then in the center there's a small platform with connecting facilities on it, and then dolphins, resting works and dolphins on the other side. And all of the connections to this, that is the power and the pipelines for loading and unloading fuel to the refinery, are under the sediment, and the refinery is located about here. Well, these are two different structures, and I picked it out because it illustrates the points I want to make today. They're local ones, local systems, and you can go down and see them anytime you want. This wharf has the advantage that you can drive a truck out there, and the operators here would very much like to drive a truck out here. They have to take a boat out, which is a disadvantage to that kind of a design. The contours around the oleum terminal look like this. This is 25-foot line, comes like this. The 30-foot water depth comes like this. And then there's this 40-foot water depth in a groove here. And here's one at 60 feet. And here's an enlarged view of that. Here's a 60-foot contour, 55-foot contour. So there's really deep grooves here and here. And then it's 35 feet here and 25 feet here. Actually, it fills in more along here than shown here before they dredge it. They'd like to keep 40 feet of depth along the side. Well, why is this peculiar scour occurring? The reason is that there's strong flows out of Carquinez Straits, as I indicated earlier. There's 1,000-some piles underneath this platform, and the sediment accumulated in the piles in the shape of a big loaf of bread. You know, it just filled in the piles, so that this is essentially a solid block out here, and the blunt end diverts the currents on either side and causes these scour holes, but there's nothing to scour out the sediment inside the scour holes. So what's needed is some kind of a structure on the end here that would make these scour holes parallel to the wharf. In addition, the piles under this trestle coming out here cause sedimentation back in this region, but not too much because of the strong currents here. So their main problem is that they just have a blunt end on the wharf, and it diverts the water away from the face of the wharf so that they have to dredge. Well, a student did a model study of the shape of a wharf end that would cause the scour to occur right next to the face. And what he did was go down to the Bay model and put in that very wharf different shaped ends, small models, and measured the velocities along the face of the wharf for the different models. And the optimum one that he came up with, a pretty practical problem, has a shape where the distance y for any distance x from the end of the wharf, this is the end of the wharf here. This distance x, y rather, is related to x by this relationship, where w is the width of the wharf here. Just a parabolic kind of a shape. That has an end that's blunt enough so that there's a velocity head given up right at the end of the tip here, and that velocity head drives the surface currents downward so that you get a downward curve like this. And there's also a little bit of a curve back here. That's the kind of flow that you get around a bridge pier, for example. It causes scour around the bridge pier. By having it rounded this way, it's not too sensitive to the direction that the current comes. If you made it blunter, it would be much more sensitive. And it definitely causes scour down in this region, a little bit beyond the tip here. And it moves, but most importantly, it moves the scour from something like this to a parallel arrangement to the face of the curve. That's a curve, the same curve, just half of it that I showed you at the Vallejo terminal. The oleum, the Standard Oil terminal, the Standard Oil Long Wharf at Richmond, in terms of tonnage, it handles the second largest amount of tonnage of any port in San Francisco Bay. It's a remarkable facility and very heavily used. Well, they had a severe dredging problem out here. This is an existing wharf already, and most of it was in this region. Was not much out here, but most was in this region here. Model studies showed that the edge of the cut, this is quite shallow out in here. It doesn't show the depth, but it's quite shallow out in here. The flow, tidal flow across the edge of the cut created eddies, which reduced the bed shear stress and promoted aggregation of the particles. So that the deposition rate was very rapid out in here, out to about, well, it was about, pattern was something like this. Model studies show that reducing the slope of this to a slope of 1 on 10, 1 foot rise to 10 foot horizontally, would eliminate that and allow the currents to flow across without eddies, which increased the bed shear stress in this region and reduced the rate of sedimentation. So one thing changed the sedimentation rate and the provided erosion. Now, a dredge operator can't cut a 1 on 10 slope. You know, they're not that skillful. So what you do is make the cut. If we drew a cross section across here, let's say, ask them to cut 20-foot treads and 2-foot risers like this. And they can do that pretty well. And then, of course, if that fills in right away with sediment, so it makes a smooth slope. Asking a company that has a wharf to do something like that is quite a request, because it means that they have to dredge a lot more area than just removing the material. This is, if I recall, this was 35 feet, and this is about 5 feet mean low water. So we're dealing with 30 feet of steps. That's a lot of sediment to cut. And you don't want to recommend that unless you're pretty sure it's going to make a difference. Well, it made a huge difference. They still have sediment problems here. We couldn't do anything with this region back here. They still have some in this area here. But this sedimentation rate was greatly reduced. It happened at a time when the regulatory agencies prevented local disposal of the dredge material. They have to now carry it to Alcatraz, which increased the cost about 5 times, cost of dredging about 5 times. So the change in the sedimentation rate was valuable to them. That's been a pretty successful project. I wish we could have touched and we'd have made it even better, but in any case, it turned out pretty well. Going back to the original picture, this wharf has a cut going out to the channel on either side. You can see the dashed line here, and that cut is tapered, as I described for the Richmond Long Wharf. Also, the wharf is oriented so that the structures are in line with the dominant currents. The currents aren't exactly back and forth. There's a spread in the direction here, but it's in line with the dominant currents, so that the shadows, if you like, of the piles, flow through the piles, does not fall in any of the area that's dredged. When that was built, we oriented it on the basis of current measurements made in the estuary. That is, we put a boat out here and a boat here somewhere and measured the currents throughout a tidal cycle so that we knew the direction of the currents. Then we went to the Bay model, and they agreed, the currents in the Bay model agreed with that, and we designed this cut in the Bay model. Well, that was built in, and there's no causeways, I pointed out, so that there's no interference with the flows. Now, when it was built, the contractor was on site, and he looked at this wharf from across the water, and he said, "Hey, that's not lined up with the Oleum wharf." He thought it ought to be lined up. I had a really hard time with him. I finally convinced him to put it where we planned it, and he did. Anyway, it was built in 1966, and in 1985, I think it was, we had a hydrographic survey made, and except for a little spot right there, it's all the same depth it was to begin with. So it paid off. And the only disadvantage is that you have to take a boat or a helicopter to get out there. That's the first super tanker wharf in the bay, by the way, the first for large, very large tankers. And it's been very successful. In view of the high cost of dredging, you can see that making a terminal that doesn't require dredging is much more important than providing a causeway for pickup truck to drive out. Well, the points I want to bring up are, if you're engaged in something like this, by all means go out and make current measurements at the location, in the area itself. Don't depend on any model. Actually go out and make those current measurements so that you know for sure that this that the orientation that you have is right. Now, sometimes it's not possible to make it. That is, there's enough variation in the currents in both directions so that you can't avoid some shadow of the piles in the area. If you do that, then, or if you find that circumstance, then you want to cant the angle a little bit so that you have downwelling at the wharf face. But normally it's not too much of a problem. You can just line it up and minimize the effect. The ships often will leave a shadow that will cause some deposition there, but that's not turned out to be as much of a problem as I thought it was going to be. There's another wharf installation up in Carquinez Straits that was done this way, and it's been 100% successful also. 2 on the Mississippi, and 1 at Anchorage, Alaska, that was modified. The 2 on the Mississippi, we were able to locate them, so that made it much easier. And the 1 at Anchorage was in glacial flour, and this turned out very successfully also. So the system works all right. Humboldt Bay, we have a situation too. This method of putting slopes in the side and maximizing the shear stress of the current turns out to be a very effective way. Now, the other method of controlling sedimentation I've described already is keeping the suspended sediment out. I missed that.
It sounds like you've had terrific success in all these consulting projects. Have you ever had any
Well,
that haven't come out as
there's some that aren't as successful as I'd like. You know, sometimes there's only that much you can do. But I'd like, for example, to have had the Standard Oil Long Wharf been 100% sediment free, but there was no way that you could keep it from settling in that corner. They're very happy with the results, but it would be nice to eliminate it all. Here's a picture of that wharf. You can see they're just dolphins out here, and the ships tie to these dolphins and load off the platform. The second one I want to describe is the one I described on our field trip. We stood on this wharf over here, and I pointed at the harbor here. Oh, this is one that I did, by the way. Turned out okay. This is a view looking from above the Carquinez Straits Bridge upstream into the harbor, into the estuary. And this is the harbor I described for you. And notice it now has an earth fill on this side, all out to this old ferry slip. There used to be a ferry slip in here also. And it doesn't seem to show on this. There should be a baffle right in there. But this is a case of trying to keep the sediment out. Now, the conditions weren't favorable. This area is drained. But as I described before, as the tide rose in this region, water flowed across this and through this and out through the porous breakwater that existed at first. And this was essentially just a sedimentation basin that let the material fall. Of course, it flowed through the piles and wave breaking apparatus under this causeway, which exacerbated the problem. And the solution was to seal it with aluminum plates all along here, and they had problems here until they built this earth fill out along that side. This is a mud flat that filled in from the gold mining activities. Well, this is a case of a harbor that was built, and you had to do something with it to fix it. The entrance was out in the deep water, which is the best location, but it's still affected by flows that flow around this and by it, so that during a rising tide, water flows around here and into this entrance and then back out. So the sedimentation pattern is a strong sedimentation near the entrance and not very much near the back. That's typical of a situation like that. If it would have been better to have had the opening somewhere in the middle, so there was a little bit of dispersion each way, but probably not that much better. Certainly wasn't worth tearing down the breakwater and building a new one, building a new entrance. That's about the best you can do with that harbor. And that's another case that I'd like to have had a lot better. They have about, averaged over the whole harbor, it's less than 6 inches a year of sedimentation. But most of it's in the entrance, of course, and everybody goes in and out the entrance. So when it fills up with mud, you have to dredge it. Still, it makes a viable harbor. Economically, it's worked out pretty well. The demand for harbors in the Bay Area is very high, so they can charge enough to keep it open. If the principles, though, that I want to illustrate are, if you close it, if you want to keep the sediment out, it's important that the walls be tight, be watertight, and that the entrance be where the suspended solids concentration is the lowest that you can get. And of course, if you can't get it in this case, you can't make it zero, so there's always going to be some sedimentation. And to minimize that, all you can do is minimize the amount of sediment that comes in. Now, one thing you can do often is to extend the entrance out to deeper water where the suspended solids are lower. And there's a harbor over on the other side that we did that on. And that does cut down the sedimentation rate. The principle, though, is keep the sediment out as best you can.
On the diagram or the picture there, above where the boat harbor is there a lot of sedimentation on the right-hand side of that?
Here? Yes, this is a mud flat, and this is a mud flat, and this is mud flat here, and there's mud flat.
What about immediately adjacent to?
During ebb flow, big part.
Just wondering what. This area here, would that be a problem for this work, just the way it looks? This is all mud flat here.
Yeah,
is
it's
there
a mud
lot of
flat.
sedimentation?
This is, this is dredged out in here. There's a lot of sedimentation back in here. But this isn't like that platform that I showed you. There are relatively few piles under. This is the one I did. This is a shell terminal. It's an old terminal. We did some oil spill studies on that terminal one time. My memory is that it's not quite oriented to the currents. I want to emphasize that the walls need to be watertight. It sounds like a simple thing to say, but it's awfully hard to get accomplished because contractors can't imagine why, if you have an opening, wide open connection here, why it's so important to have the walls tight. Up at Noyo Harbor, at the Noyo River, the harbor district built a harbor by excavating valley floor. They made a basin in the valley floor right next to the river. And to separate the harbor from the river, they put in a wooden wall 1,000 feet long. And I designed the wall and the entrance and wrote with emphasis, the wall must be watertight, and filled in and so far down into the sediment to eliminate the problem of the river coming in. In that case, the river during freshets, during storm runoff, carried a lot of sand and gravel as well, and you didn't want that in the harbor. Well, I wrote this letter, and like most of these things, it's a long time between the time that you do your study and it gets built, and a longer time still before there's some experience with it. Well, I got a call from the design company that I'd worked with saying, can you come down today in San Francisco? So I went down, and as I walked in the door, the principal of the firm said, now Ray, he says, don't say a word. I know that in my file there's a letter that says the wall must be tight, but we have a problem. And it turned out that the contractor dug a ditch deeper than the bottom of the wall, then built the wall in the ditch with on piles. And he did a nice job of building a wall, but he left a 2-foot wide slot under the whole length of the wall. When the next freshet came along, there was a huge amount of gravel in the harbor. And it was a serious problem. So they wanted to know if they could just put a plastic curtain up or, some low-cost method. Turned out they had $10,000 to fix it with. And so I suggested that they get prison labor, which turned out not to be too good a recommendation. But they advertised for bids, and I recommended that they put sack concrete. You put wet concrete in gunny sacks, jute sacks, and place them like stacking cordwood down in this trench. The trench kept itself washed out. Once it did that, it was on the outside of a bend, and so they advertised, asked for bids for someone to do that, and a local contractor said, oh, I'll do that. Well, he apparently had never worked with sack concrete before, so he put dry concrete mix in a sack and then just threw them in off a barge. Well, you can imagine what happened. The cement washed out of the sand and gravel in the concrete, and it was just one mess down there. So there was a lawsuit, and it got pretty ugly before it was through. And we finally got divers to go down and chink up the holes with sack concrete to fix it. So you can see that it's not really a trivial matter. If you don't get it built right, then it's hard to fix later. I think that's all of it. Oh, this is, I've forgotten which one this was. I think this is Pittsburgh. Yeah, this is the Yacht Harbor at Pittsburgh. And it has the features that I described earlier. The rounded corners that tends to keep this wall clear. If you don't do that, then a fillet fills in alongside the wall. This is the bottom. A fillet will fill in like this along the bottom edge of the wall. And by using these corners, you can reduce the fillet there, and particularly right in front here. The direction of strongest current was this way, so we put in a baffle to prevent circulations of this sort inside of the harbor, which you get without that baffle. And we tested this in the bay model with the tidal currents and measured the rate of flushing. One of the problems in an enclosed harbor is that if there's a waste discharge in there, the water quality can deteriorate. So whenever you have an enclosed harbor, it's important to specify that all the head tanks are pumped out, no discharges in there, and that the fueling facilities not leak any oil or non-volatile materials onto the water, because you want to minimize the amount of circulation in there to minimize the sedimentation rate. Now, in some harbors, it's necessary to provide a pump that can be turned or a gate that can be opened so that you do get circulation in there, so that if you do get an algae bloom, you can open that and let and flush the algae out. That's normally not a problem unless the harbor has a part that's a long way from the entrance, so that where the residence time is very long. But if you do, then you have to have some kind of a pump. It's important that you be able to block it off, however, so that you don't have circulation during periods of high suspended solids concentration. Usually there's algae bloom in the summer when there's low flows, and you need the circulation then, and the suspended solids concentration is low, so it's not a problem. But you want to be able to close it off during periods of high suspended solids concentration. We usually do a residence time computation, either model it physically or in recent years mathematically, to determine the residence times in the corners and determine whether there's an algae going to be an algae problem. We have a little model that describes algae growth, maximum algae growth rates. Well, so much for enclosed harbors. Oh, no, there's one other thing I should say. Often you can justify the enclosure because of needs for protection against waves, not just sedimentation, but against waves. And in the design of these, at least these outer breakwaters, it's important that you calculate the waves that are liable to impinge on it, and the wave height and the tide together shouldn't overtop the wall with solid water. The top elevation of the wall needs to be high enough so that only spray goes over the top. The boats inside can stand spray, that doesn't bother them. But if you have significant volumes of water coming over the top, then you can have damage inside. So part of the process of designing a wall of this sort is to calculate the height of the waves that you get 1% of the time or whatever they're willing to get, and estimate the height of rise of the waves. We discussed this a lot in 260, so you can handle that all right. The problem is that every foot rise in the height of the wall costs a lot of money. So you're always torn between wanting to have it higher and wanting to keep the cost down. If it's an earth breakwater or rock breakwater, then the cost is even higher per foot of rise, or concrete breakwater. Sheet pile isn't so bad, or wooden sheet isn't so bad. I missed something there.
Is in that equation there,
Uh-huh.
is W the depth of the water?
W is the width of a hypothetical pier. It's this is half the width of a pier. Remember in the, oh, well, here.
What's the radius of that?
The same, well, that's the one we visited at Vallejo before the bridges were done. You can see the curves on the side there and the baffle in the front. And the baffle we looked at inside. Okay. This width here is this width. So for the corner, you want just part of that. The corner comes like this. You follow me? You're just looking at half of it. Well, to summarize then, the points I want to leave you with are, first of all, know your estuary, generally. That's really important. And it's worth spending some time looking at hydrographic surveys over a period of time to see what the trends are, finding out what the sediment composition is, what the supply of sediment is to the system, and what the wind patterns are and the seasonal changes in freshwater outflows and winds and so forth. Before you ever get started, it always pays. And I might say, always go to the site yourself. Don't depend on someone else to look at it. I think that's the best advice I've ever given myself, is always go to the site, because other people see different things. They're not concerned with the same sediment problem. Well, going to the site gives you a lot of information. It tells you what questions to ask, what's liable to be the problem. And if you can, fly over and look at it, or if you can't, drive around it and look at it. And walk out to the proposed site. Really take a good look at it. You can learn a lot just going there and looking at it. Then the second thing is determine what approach you're going to take to controlling sedimentation. And if it's keeping it moving through, then make plans accordingly. If it's enclosing the harbor, then you want to look for the place where the suspended solids concentration is lowest in the incoming water and put your entrance there. And if necessary, extend the entrance out into the system. All of these things cost, so you're going to be faced with optimizing your system according to cost. But usually the cost of dredging is so high and so continuing that you have some flexibility there. Then the last thing I want to say is I find it useful to model a system. After a while, you get so you can anticipate what's going to happen. You can make some judgment. I've made some phenomenal guesses, but they're really only guesses. And if somebody's going to put a lot of money on your guess, you better have all the support for that guess you can. And modeling is not too expensive now. We have computing machines that are pretty inexpensive. So I strongly recommend modeling. And the next thing I'm going to talk about is models. Modeling a system. And even if you don't make an elaborate model, make some kind of a computation and see what's to be expected, and look at the numbers and see whether you're talking about a serious problem or a not too serious problem. Modeling isn't the answer to everything, but it's a very useful tool. And of course, the model's only as good as the information you put into it, which means current measurements, knowing what the tides are in the location, and most of all, knowing what the suspended solids are. And that's where you run aground modeling. So let me wrap this up and start talking about modeling. Before I do, are there any questions about controlling the system?
Specifying this curvature on wharf ends and on corners of
Uh-huh.
marinas, do you have a lot of trouble getting contractors to match that?
I thought on the first one, I think the first one that we did that way was Pittsburgh Marina, the one I showed you the little outline of there. And I thought that would be a problem. And then the specifications, I gave the XY offsets, you know, I gave them a table, not just a formula. And I had a couple of phone calls, you know, and asking, well, how do I do that? And we talked about it a little bit. And then since then, I've never had a question. They've done it, and it hasn't added to the cost particularly. It uses a little bit less pile. Sheet pile costs about $1,000 a running foot, but not that much less. I don't think that's.
I can imagine there's somebody out there replacing sheet pile and to get the angle of the sheet pile about right.
Yeah, I think what they do is put a pile out there and put some strings on it, and just measure from the pile. But they've all done it, and they all come out looking nicely. The wooden ones that we saw are the only wooden ones that I know of there. The others are driven sheet pile.
Did they fix that one that was dead and they put on a curved end one? The one that we were looking at earlier?
On the wharf? No, they never did that. That's a Union Oil Company. They never did it. They decided dredging was cheaper. It would have been a concrete shell kind of a structure, and or a sheet pile. But they opted to keep dredging. So sometimes, you know, you design things and they don't implement them. I've designed lots of harbors that will be built someday, you know, and when they're ready. There's a quarry over at in San Rafael, hard rock quarry. And they found a big, it's actually a igneous intrusion, I think, a big hard rock deposit, and they've excavated down into it. They're down to 100 feet now from the top, and it's they've left a shell all around the outside, and it's right up against the edge of the bay. So we designed an entrance to that hole so that someday they can make a yacht harbor out of it by just cutting that entrance through to the bay. The problems there were, that's a very tight enclosure. The problems there were that those solid vertical walls make it subject to resonance. And if you have much resonance, that moves the docks back and forth and the floats in the middle. And when it's 100 feet deep, there's no friction to speak of inside there. So we specified that the floats be anchored to the walls and be allowed to move a little bit either way. That was an interesting exercise in estimating the frequency and so on of the harbor. But it's going to be built someday. When they finish quarrying rock out of there, they'll put a harbor in and put condos alongside it, and, you know, and make a lot of money. I want to talk about, well, hardly time to get started on models. I'll start on models next time.